Guess it doesn't like to go all the way bottom, does it? All right. Try it up there. Okay, so basically, the radio involves transmission of information by uh, generating and receiving radio waves with some information on them. Um, CW is the basic example where you turn it on and off. Digital modes do a similar thing, although usually modulated with a tone or multiple tones. And then in the voice or audio case, you're using voice audio in order to modulate it, either AM or FM, or in some cases, phase modulation. The electromagnetic waves are composed of an electrostatic field, which we call the E field, an electromagnetic field, which we call the H field, and they're perpendicular to one another. If you see in the little picture, uh, they're showing the red electrostatic field. In this case, it's a horizontally polarized wave. The magnetic field is 90 degrees from that, or vertical. We mostly deal with the electrostatic field. Now, if you have I guess, a magnetic loop, it's receiving the electromagnetic wave. But if you've noticed on that, did you see the video last week?
Mm-hmm.
And they showed how the magic of it releasing the uh, electric, uh, electrostatic wave.
Mm-hmm.
Uh, and that's mostly what we deal with. I can't tell you much about a magnetic loop other than they're getting popular, they're expensive, uh, they're extremely narrow band. So you have to be able to tune it if you want to move around in frequency. They won't cover an entire band, even the narrowest bands.
So what's the advantage of it then? Is there any?
Well, they're small. I mean, you can put it in a room, put it in the attic. Um, Apparently, they have pretty good gain, and especially people in HOAs or apartments or something like that. You can sit on the balcony. Um, I mean, there's a lot of advantages to it. I mean, a lot of people can't put up a tower.
Right.
Well, I guess we'll do this one. It's a lot of repeat. Maybe we will. Thing on the internet. But while we're waiting, the key thing is that 90 degrees apart between the electrostatic and electromagnetic. You don't have to remember those. I like their electron, their atom there.
All right.
Huh?
Don't hesitate to donate.
Yeah, they like their money. Uh, that feed horn they showed on the dish antenna is actually an impedance transformer, which is what we would use with a regular wire wound transformer for most of our antennas. But it does the same kind of thing. I don't know what the natural impedance of that dish would be, but that's how you match it to the free space. So which is 377 ohms. So it's going to match 377 down to whatever that is.
Okay.
Okay, so what are the two components of a radio wave?
See.
What's the relationship between the electric and magnetic fields of an electromagnetic wave?
Indeed.
Right angles to each other. Yeah.
Yep.
A is true.
A? What was A?
They, no, they both.
No, they don't. They're together. They stay in phase. Well,
So,
sort of in phase.
so they stay in opposite phase, but it's still a phase.
Right.
Right. It doesn't change.
Right.
Right. Okay. So I don't know if we talked about frequency, but it's the number of complete cycles per second, which means polarity reversal of the current. We measure it in hertz, named after old Heinrich Hertz. Use the capital HZ. That's a trick question. They'll give you 4 variations, and you have to pick the one with the capital H in it.
Because it's a proper name. Is that what?
Because it's proper name. Wavelength is the distance the wave travels in one complete cycle. Assuming that it's traveling at the speed of light. Now, when you get to it actually traveling in wires, it's a little bit slower. So there's velocity factor that you apply. So you'll see a 0.95 come up in some of the calculations, because that's typically what it would be in a bare copper wire. Now, it's much slower in coax. And if it's insulated copper wire, it's a little bit slower because it changes the dielectric.
Is that because of the resistance?
No,
No.
The dielectric changes, so the capacitance changes. And the speed of light is 299,000, blah, 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 or approximately 300 million meters per second, which is what we use, is close enough. And if we deal frequency in megahertz, then we can cancel out the million and make it 300 versus whatever the frequency is in megahertz. So it makes the formula real simple. And it only travels at that 300 million in free space, which means, and basically it means a vacuum. To calculate it, and we use the symbol lambda, which is that funny looking thing. We divide the speed of light by the frequency, and that will give us the distance or the wavelength. So instead of doing the 300 million, with the frequency in hertz. Like I said, we reduce it down to 300 over the frequency in megahertz. Conversely, if you swap it around, if you want the frequency, you divide 300 by the wavelength. So you can go back and forth just by reversing the formula. The lower the frequency, the longer the wavelength. The higher, the shorter the wavelength. Test question.
It kind of makes sense if you look at a sine wave.
Right. And if, look at the way you divide it, the
Mhm.
higher number is going to make it shorter. A little example here. The wavelength for about the middle of the 40-meter band, which would be 7.150. It goes from 7 to 7.3. So that comes out 41.95 meters, and we call it the 40-meter band because it's an approximation.
Okay.
In this example, we're doing the frequency for the 20-meter band, and it comes out 15 megahertz. It's actually 14 something in practice, the frequencies. 14 to 14, might be 0.3. I actually can't ever remember all those. But unfortunately, some of them are on the test.
For the practice test coming in handy.
That's why you have the little cards. What is the velocity of a radio wave traveling through free space? Speed of light. What's the approximate velocity of a radio wave in free space?
3 times 10 to the 8.
Huh?
6.
Well, it's 3 times 10 to the 8 meters per second.
Yeah.
That's all I.
Three times 10, right?
Yeah. But they're using 300 to the 6.
Well, and that way it comes out megahertz.
Megahertz.
What's the formula for converting frequency to approximate wavelength? So in other words, you're solving for wavelength.
Would be D.
There's Ernie. Which one are you going with? Oh, okay. All right. What's the relationship between wavelength and frequency?
D.
Yep.
We're doing test questions.
I didn't hear you.
We're doing test questions.
Oh, okay.
I'm sure you know all these.
Majority of them.
Does everybody know Ernie?
No. I'm Aaron. For K1CPO. Steve. Roger.
Yeah.
He's going to help us with our hands-on a little bit later. And Dave is got his radio. So
He's gonna break by.
no,
Oh,
he's working. So he'll answer if there's nobody around. Otherwise, he get in trouble. But we can also talk to Michael on the KSC repeater. He's got his radio, and I checked with him earlier.
Okay.
Okay. The relationship between wavelength and frequency. That would be.
The shorter end.
Sounds good to me. Okay. Radio frequency is, as far as the exam is concerned, a radio signal of any frequency or any mode. It's just kind of a generic term. Why that's a question, I don't know, but I guess they have to fill up the 400 and something questions with something.
Well, they cut down this new list just come out. They got rid of 40 questions starting this July.
Oh, for the general?
Yeah.
Oh, I hadn't compared it yet. I've got to do that.
Hmm.
Okay. We use both frequency and wavelength when we talk about radio signals. Basically, wavelength to represent bands of frequencies because it's easier than talking about specific frequencies. When you're talking about a particular band, then you might talk about it being, 7.074 or something like that. And they're kind of used interchangeably back and forth. That's why you need that formula, but you can pretty much do it in your head to get close. 20 meters into 300 is about 15. This example, the 2-meter band goes from 144 to 148. So if you do the math, it comes out 2.03 meters. So these are always approximations. They're never exactly the right number. Usually it's off the band. But, that's something that's you get used to. It just becomes kind of second nature if you played with it for a while. We split up this range of frequencies that we use into these sub ranges called medium frequency, high frequency, very high frequency, ultra high frequency. And I guess now they're doing super high frequency and whatever the one is beyond that. I'm not sure. And also, I guess, low frequency.
For low.
Yeah. That's the club just put up 160 meter wire out at KSC.
Listen to submarines or something.
I don't know, but the 630 and what 1200 something meters.
Yeah, it's 135 kilohertz one. That's the very low one. I mean, you're allowed 1 watt. That's radiated power.
Well, if you got
it's what the utility companies use for transmitting data. That's why you have to file a claim or get permission from the utilities to use those ultra low frequencies.
I did not know that.
Now, you have to sign up before you can use it.
Okay. Well, supposedly that low stuff is getting popular. I don't know.
I don't know. Never tried.
Okay. This you probably can't see too well, but it's just showing it's a reduced form of these other band charts, just showing the technician privileges, where at HF, you have phone and data and SSB, CW, all those on the low end of the 10-meter band. That's the only HF where you can operate phone. For VHF and UHF, it's pretty much the entire bands, except for that 1.25 meter, which I don't know who uses that other than, I guess it's communications repeaters mostly, isn't it?
I don't.
Back channel. And you're limited, I believe, on these VHF, UHF to 1500 watts, 200 watts on the HF. Now you can do CW on the other HF bands if you know CW, but it's not required anymore. But I understand that's getting popular again, particularly in the QRP world. This is this showing what frequency ranges are. Medium frequency is 300 kilohertz to 3 megahertz. So the 160 meter band is going to be in there. HF, which is what we normally do, particularly phone SSB, is 3 to 30. These all go up by tens. VHF is 30 to 300. That one will come up again in the safety because that's the maximum exposure frequency band. Your body is most susceptible at 50 megahertz. So that entire 30 to 300 is the minimum exposure you're allowed. And UHF is 300 to 3000. Okay, in addition to frequency, which of the following is used to identify amateur radio bands?
Right, we didn't talk about the other two, so I'm guessing.
Yeah. Uh-oh.
Not on that, Joe.
Oh. Clicked on the wrong spot. Good. What frequency range is referred to as HF?
See,
103.
HF.
okay, so
3 to 30. The 40 meters is 3.5 megahertz. 10 meters is 29, what? 28 to 29.
We need something.
Yeah. I don't remember them either,
I don't remember.
but you should. You've been doing it for years.
Doesn't mean I can, it shows up in your radio.
Oh,
Predetermined,
huh?
predetermined selection.
Yeah.
Yeah.
I skipped ahead, but VHF is 30 to 300. Like I said, that comes up on the exposure calculation. But it's also a question in this group. What frequency range is UHF?
No.
What does the abbreviation RF mean?
okay,
See, I told you they had that question, but I don't know what it serves. Okay, propagation modes. This is fun stuff. Hopefully you know more about it than I do, Ernie.
A little bit.
The atmosphere can refract or bend radio waves depending on the angle and the frequency and solar conditions, how much ionization there is, which is oxygen atoms in the upper atmosphere. When there's enough high energy particles hitting them, can displace electrons and create positive and negative ions. And those interact with radio waves and can bend them, like light gets bent through different types of glass or other material because of the diffraction index, refraction index, I should say. So it's a similar thing to the way light works, because light is just very high frequency radio waves. So some of them will actually bounce off. Some will go straight through, like UHF and above. Typically, there's no refraction. At least is my understanding.
That's very little.
Some on VHF. So they're not propagated, which means they're not, you don't get any sky wave where it gets refracted and bounces back down and then bounces up off the earth, and maybe do it multiple times. You can get all the way around the world sometimes.
We call it skip anymore.
That's called the skip, is how far it goes.
Yeah. And unfortunately, when you're doing that, that region in between,
You're skipping it.
nobody hears your signal. Unless it's a very broad band and it's scattering all over the place.
so it's kind of like driving up 95 with an FM radio station on, if two towers are transmitting two different radio stations, they kind of alternate as you get further away from one and get closer to the other.
Yeah. Okay, so most VHF, UHF is what we call line of sight, which means you have to be within visual, assuming there were no buildings, trees, whatever, okay, that you could see the other antenna. And there's a formula for calculating that based on the radius of the Earth and how high the antenna is to where the visual horizon is. And that's this 1.23 times the square root of the height of your antenna. So if you've got a handy talkie and you're a tall person, say it's 6 feet above the ground, then it would be the square root of 6 times 1.23, and that would give you how many miles to the horizon. Now, if you're talking to somebody who's the same height, okay, you got twice that distance. So it's yours plus theirs, wherever they are. Now, because there is some refraction of VHF, they come up with a fudge factor, and they use 4/3 of the Earth's diameter in the equation. And it comes out to be, it's actually the square root of 2 times the height in feet. So it's 1.414 times the square root of h. So it gives you about 15% more. But does that only apply to VHF or also UHF?
About to say they call, when we were negative, 5/4 what we used.
Yeah, the latest stuff I read said 4/3.
20% more.
I think it's a fudge factor.
Yeah.
It's approximation. But basically, because of the refraction, the waves can actually travel farther, and we call that the radio horizon as opposed to the visual horizon. This little diagram showing, here's what that distance would be when you calculate it, and when you're talking to somebody else, it's the sum of the two, which would be the total distance.
So with lower frequency travel farther, like if you're in the HF range.
Ground waves, they go out. They've been more UHF and
Yeah.
VHF.
Yeah, HF works different. And there's a big difference in frequency here. So,
Yeah.
okay, why is the radio horizon for VHF and UHF more distant than the visual horizon?
See.
Okay. Why are simplex UHF signals rarely heard beyond their radio horizon? So what they're referring to is you're not going through a repeater. You're talking on the same frequency as somebody else with another radio.
The reason they say rarely, because sometimes you do get a reflection, or tropospheric conditions will make the radio wave go around.
Should we see
Hmm.
on this one?
On the other, see what you.
Usually not propagating.
There's always exceptions to everything. Okay, multipath. That's where you can have multiple signals arriving at your receiver, even though they came from the same transmitter, because they can reflect off of buildings and other things. So you get that signal coming 2, 3, 4 different ways, and they get there at different times. So they can add or they can subtract, and they can cause echoes, very short echoes, but definitely cause some distortion. Just by moving a few feet one way or the other, it means you'll change the pattern. And that's where, and that can cause the signal strength to vary greatly depending on where you're at and if you're moving, which is the picket fencing Usually you see that if you're mobile in a car. And because you're getting multiple things, it'll kind of sound like you're going by a picket fence, da, da, da,
Copy.
because it comes and goes and comes and goes. Uh, when you're doing digital transmissions, uh, they don't work well in those conditions. Because in digital, you either have the full signal or no signal. There's no noisy signal. Whereas with single sideband or AM, I mean, even if it's full of noise, you may still be able to understand what somebody's saying. With the digital signal, you get a good signal or you get a no signal.
Well, it's like satellite radio, I guess.
Yeah. This is just a picture showing potential multipath off of these big buildings. Now, I guess we don't see that much around here. There aren't too many things to reflect off of.
It's like, Verizon is 5G.
It may be. Okay, why do VHF signals sometimes vary greatly when the antenna is moved only a few feet?
Don't you see?
What's the meaning of the term picket fencing?
B.
What'd you say?
I said B.
Oh, okay. I don't hear well. What effect does multipath propagation have on data transmissions? There's data, not voice.
Delta.
Yeah, I was gonna say here.
Repeater access. Normally, you're talking line of sight to a repeater. They're typically on very tall buildings or towers. I guess the highest one around here is the NASA repeater on top of the VAB. It's 526 feet. So if you do that calculation, the line of sight for that is about 30 miles, 40 miles. Uh,
1,000 footers.
huh?
There's no 1,000 footers around here.
Yeah. One
Maybe.
Up in, Bidwell or on, around 50 left. Bidwell.
Bithlo?
Delta.
That's about 1,000 feet up.
Really? Most of them locally or what's broadcast court?
It's about 370 feet or 400 feet, something like that.
Yeah.
And one down in Melbourne's like 400 feet.
Yeah, I can't get that with my handy talkie. At least not in here.
Yeah.
Now there's also an indirect path where it can kind of like multipath reflect off of something else that you don't have a direct line of sight, and you may be able to get the signal to bounce off of something and still get to what you can't see. I'm not exactly sure how that works or how to explain it. I haven't seen it. I'm just going by what they tell me. There's also knife edge diffraction, which I'm familiar with in optical stuff, where you have a very sharp edge, like a razor blade or something, and light will bend around it quite a bit. And I can understand it around the edge of a building, but supposedly something like a mountain peak will do it. I wouldn't consider that a sharp edge, but I guess it works. So with knife edge, you can theoretically get to an antenna that you can't see that's on the other side of that mountain. And then we got absorption. basically anything with water in it, vegetation, people, absorb UHF and microwave signals. So they don't work good in the rain. Anything with a lot of water. It's just a little thing showing typical repeater access where it's up on top of a mountain and you can't see the other guy, so you go through the repeater. When using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the direct line of sight?
Bravo.
This is one showing knife edge diffraction where it sort of bends the wave, and you can see it down here. They call it the geometric shadow. Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations?
I'd say A, but B is pretty funny.
Yeah.
Fair
Fair
And
enough.
we haven't got to satellites yet. What's the effect of vegetation on VHF and microwave?
B.